Hello Year 12 and welcome to our second video here for motion. In our previous video we looked at average velocity, describing that as a change in displacement divided by a change in time. Now if we can think back to our calculus days, you might remember that we initially introduced calculus as the gradient of a chord between 2 points as those points get really close together. Right? Now we want to talk about velocity here, not an average velocity but instantaneous velocity, and that means what we're after is the gradient of the tangent to the curve at some point, right? Not the chord, not between 2 points, but actually as a tangent, so we get an instantaneous velocity. And this is the derivative of the displacement function. Right, we know how to differentiate things. A little bit of slightly new notation here. My velocity, v for velocity here, is dx onto t. Differentiate x with respect to t, and we can write it as an x with a dot above it. There you go, something different. X with a dot above it refers to velocity. It's the derivative of x with respect to time. Okay. We also need to talk about speed, and I think we've probably spoken about that in the first video there. Speed is a scalar quantity, so it is the absolute value of the velocity. All you do to calculate the speed is calculate the velocity and ignore the positive or negative. Yep, absolute value. Rightio. Now, example 3 here is from the example above. What was the velocity with which the ball hit the ground? We need this function again. Now, remember that it was x equals, I think it was 5t outside of 8 minus t. Now, I know that my roots are at 0 and 8, so I'm going to find the velocity when t equals 8. But this means I'm going to write it like this, x dot equals, now I probably should have expanded this out. Let's do that just over here. I'm going to say it's 40t, because I don't need to do the product rule to do something like this. 40t, that's equal to 40t minus 5t squared. And when I differentiate that, I get 40 minus 10t. Now I'm going to say let t equal 8. Therefore, my velocity equals 40 minus 80 is negative 40 meters per second. There we go. That's the velocity with which the ball hit the ground. It was moving at 40 meters per second downwards. What was the speed at t equals 4? Well, remember absolute value, but nonetheless I'm going to say that equals, at t equals 4, I'm going to say it is 40 minus 40 is equal to 0, so I don't actually have to worry about the whole positive and negative thing here. At t equals 4, my velocity was 0. Think about this. My ball has flown high into the air, and it's reached its peak. It's stopped going up. It's just about to start coming back down again. But at that point in time, very briefly, or instantaneously, it's stationary. Like a pen or a stapler. No, not like a pen or a stapler. It is stationary at t equals 4. My velocity and thus my speed are both equal to 0. Now there's a little explanation here of vector and scalar, but we've already spoken about those a few times. When is my particle going to be stationary? Well, it's when the velocity is 0, when the derivative of my displacement function equals 0. We've done a fair bit of that before. Yep. So you differentiate, let that equal to 0 and solve it, right? And that'll tell you when it is stationary. Acceleration is a change in velocity, right? If you are speeding up, then you have positive acceleration. If you are slowing down, then you have negative acceleration. You can still have a positive displacement. You can still have a positive velocity, but be slowing down. Okay, have a negative acceleration. Rightio. That's the second derivative of the displacement function, or the derivative of the velocity function. And this time we write it as an x with 2 little dots above it. What do you know? There we go. That's very, very exciting. Now we've got another example here. Consider this particle here moving according to that function, the same function we've looked at before. what is the function that describes its acceleration? Well, I'm going to say that x equals, I'm going to write it back out like this again, 40t minus 5t squared. My velocity is 40 minus 10t, and my acceleration is equal to negative 10. Right, negative 10, we write this as meters per second squared. Sometimes it's written like this, meters seconds to the negative 2. I don't know why. Meters per second squared, or meters per second, if you like. Now, that's the first part done. Good. Compare the graphs of displacement, velocity, acceleration. First of all, let's draw this. I shouldn't do that. No, but I'm going to. There we go. So, remember that my sort of, if you like, my dependent variable is x in this case, t. And we get this thing going on. That is my displacement function. Right, that's my parabola. There's 8, and that's 4 is my axis of symmetry. I'm going to scroll down. Next, I'm going to draw. I'll try to line up as best I can. This is t. This time it's v. I'm going to call it v. We could call it x with a dot above it, or dx by dt if you like. Doesn't matter. Now, what's happening to my velocity? Well, here's my velocity function. It's 40 minus 10t. Okay. Now, we will find that we get this going on. It's going to be 40 here, and negative 40 there. Just extend that axis down a little bit more. Okay, and this point here, that's a 4, right? Remember we looked at that before, that at t equals 4, my velocity was equal to 0. Now, what does my acceleration look like? I've got just enough room, I think, to draw another one here. T, and I'm going to call this A for acceleration. Okay, negative, oh, boo. I really should have thought about that. I'm going to have to draw my axis up here. That's my time there. And my acceleration is a constant negative 10. So just look like this. Now we said it was equal to, so I'll put my little close things there. I suppose I should do those. Because it's equal to. Right, that's at negative 10. So there we go. We have a constant acceleration, a linear velocity, and a quadratic displacement. Right, yep. Wonderful. Now, units of acceleration, we've talked about these, meters per second squared, or meters seconds to the negative 2. It's a vector quantity. Now, I've got one more example to look at here for this video, I think. Yes, this is my last example for this second video. Got a slightly more complicated function now. When is the particle's acceleration 0, and what's its displacement and velocity at that time? Well, so x, my velocity, right, let's do this first, is 3 times the third is 1. So you get t squared minus 12t plus 27. And my acceleration is equal to 2t minus 12. Now I'm going to say let my acceleration equals 0, therefore 2t equals 12 and t equals 6. So that's when the acceleration is equal to 0. That's at t equals 6. Now I'm going to substitute that into my displacement and velocity functions. Let t equals 6, therefore x equals a third of 6 cubed. Good heavens. Third of 6 cubed. Well, I guess that's 2 lots of 6 squared. That's right, I can manage that. Minus 6t squared. Oh, sorry, 6 by 6 squared. Oh, 6 squared plus 27 lots of 6 minus 18. You know what? I am not going to do that in my head because I will get it wrong. So here's my trusty calculator, right? 6 cubed 6 cubed divided by 3. That's how I prefer to do a third of 6 cubed. Now I'm going to go minus, well, it's minus 6 cubed again, isn't it? 6 by 6 squared equals plus 27 by 6 equals minus 18 equals, oh, my velocity equals 0. There you go. So my acceleration and displacement are both 0 to equal 6. And also, I'm going to say x, my dot, my velocity is equal to 2 by 6 minus 12 equals 0. They're all equal to 0. Now, that doesn't have to happen, but it does in this case. Right? At t equals 6, my velocity, my displacement, and my acceleration are all equal to 0. There we go. Hope you enjoy that. I'll see you in my next video.